in this section we will cover power series, we will see what it is, and we will realize it's very simple and fun, and we will be applying a ratio test a lot. So what are the power series? This is one example of a power series. Up to now we were dealing essentially with the series of numbers, but now we realize we can introduce some variables there. So here we have a series of this expression Cn are the coefficients, so those are real numbers, and x is a variable to power n. So you see here, if we write a little bit, we see that the variable is put to a power. So that's why it's called power series. So x is a variable. We will see why is this interesting. Maybe more interesting than just having the series of numbers, because this is a little bit more general. So you see that it's called power series because we have power, our variable put to a power, and then C0, C1, C3, C2, those are the numbers, real numbers, constants. What we will be interested in general with power series is to find for which values of x the series will be convergent and for which values of x the series is divergent. Essentially, we want to know interval of convergence or divergence of the series. Interval meaning for which values of x needs to be in which interval so that the series is convergent. So that's our goal, having the series in this shape with a variable, and then trying to find interval for the variable x in which the series will be convergent. And to do that, to find the interval of convergence, we will be using the ratio test all the time. So again, a little bit of preliminary result just to introduce the new words. So the domain of the function. So we realize that this series, power series, is like a polynomial. It's like a function of x. Obviously, it's not a polynomial because this keeps going forever, but it has a variable to some power, so it resembles a little bit a polynomial. So it looks like a function of x because x is our variable. So in general, when we have a function, we want to know what's the domain. In this situation, the domain will be all values of x for which the series is convergent. So domain is the values of x for which the function is well defined. So here we will just have infinitely many things, so that's why it's not a polynomial. So one example here, a funny one, is if I have a series of x to power n. So essentially this series, we already saw this series. So we have a first term is 1, and then we have a ratio that is equal to x. So this is a geometric series with ratio x, and we know from the results on geometric series that a geometric series is convergent whenever the ratio is smaller than 1 in absolute value. So this means that this geometric series is convergent for x between -1 and 1 and diverges for all x outside of that interval because this is a geometric series. Now, since it is a geometric series, we also know how to find a sum of the geometric series. So the formula for the sum is the first element, here is 1, divided by 1 minus the ratio. Here the ratio is x. So you see, because we know that this is a geometric series and we know the formula for the sum of the geometric series, we are able to write this. So for x's between -1 and 1, this power series, which is actually this geometric series, is convergent, and actually is convergent to this particular function. So this is funny. We are able to equate this series here, power series, to a function, because this function here, we know it already, and it's defined for all x's different from 1. But the series is convergent and equal to this function only for x's between -1 and 1. So this is interesting. We have equality between a function and a geometric series, but only in an interval. Outside this interval, this function here is fine. For all x is different from 1, it's fine. But this series is divergent. So for x is outside this interval, this equality doesn't hold. So this equality is true only for x's between -1 and 1. So this is particular. So we have a power series equal to some function for some restricted values of x. Very interesting. Obviously, we can substitute now any value of x between -1 and 1 and get a numerical series, which is geometric, obviously. And we know also the sum, because this is the formula for the sum of a geometric series. So basically, let's say we take x equal 1 over 2 just for illustration purposes. So we have this geometric series, and we know that it is convergent because the ratio is smaller than 1 in absolute value, and we have a formula so we can compute the value of the series. Here is 2. Now if I take x outside of the interval of convergence of my geometric series, now this equality doesn't hold for those x's, even though this function here is defined, but the series is divergent, so the series is no longer equal to a function when we are outside the interval -1, 1. So if I take, let's say, x equal 2, which is outside the interval -1, 1, series is divergent, because I would have a divergent geometric series. So this series is equal to nothing, right? It's just divergent, doesn't have any sum, because it keeps increasing forever. So you see that for x is outside the interval of convergence, the series is divergent and it's no longer equal to any function. So this is really interesting here. A general form of a power series, so you see here the difference is I have x to power n, and now we have x minus c to power k or to power n. So essentially this is a little bit more general, and the c is a number, obviously, and it's called a center of the series, of the power series. So this is just a little bit more general as writing. So here the center is c. So let's say I have x minus 5, so c will be 5, so center of the series will be 5. Here I have x minus 0, so the center of this particular series is 0. It's just an observation. So this is a general form of a power series, and we see that x minus c is the expression that is put to different powers, so that's why it's called power series. Obviously b0, b1, b2, b3, those are numbers, those are coefficients. Some conventions, what we know is that we will say for k equals 0, anything to power 0, we'll consider it as 1, even when x is equal to c. So what happens with x is equal to c? So I'll have here c minus c 0, c minus c 0, c minus c 0. So everybody here will be 0. And then I'll have b0, the first coefficient. So my power series will be convergent, and the sum will be b0. So what we just observed is at the center of the series is always convergent. So that's just an observation. As we said, x is a variable, so this is a function of x. This series is a function now of x. And the domain is the interval of convergence. So values of x for which this series converges. How do we find the interval of convergence? Well, we will use the ratio test. That will be our test that we will use almost all the time. For all of our power series, we will mainly use ratio test. And once we use the ratio test, we know that we will have an interval for absolute convergence of the series, because ratio tests, when we have convergence, it's going to be an absolute convergence. So this will be very interesting application of the ratio test. So how it works? Well, if I have a power series, there will be three possibilities when we apply the ratio test. Either our series will converge absolutely because we are using absolute ratio test, so if it's convergent, it's going to be convergent absolutely. It might converge absolutely for all values of x, meaning whatever x I put here, the series that I get is convergent. Wow, so that's one of the possibilities. So any real number for x is in the domain of convergence, so in the interval of convergence. We call radius of convergence the half length of this interval. So obviously this is all real numbers, so we will say that the radius of convergence is infinite. Now, in some cases, it might happen that the series converges only at the center. So if I put x equals c, that's the only value of x for which series converges. It might happen. So in that case, the series converges at the center and now nowhere else, and we will say the radius of convergence is 0 because it's just a dot. And the third option, which will happen most of the time actually, is we will have an interval of convergence. So our series will be absolutely convergent in an interval for certain values of x. And you see here we'll have x minus c, so c is the center of the series, and this expression will need to be smaller than some number r. So r is actually the radius of convergence. So obviously we need to deal with this inequality in absolute value, so we rewrite it. So x's will belong to an interval center minus radius, comma center plus radius. So it will be in an interval. And series will be divergent outside. So another thing that we will need to consider, because this will come automatically from the ratio test. We'll get this interval automatically from the ratio test. Now the only consideration that we will need to have also is to check what's happening at these end points of the interval. This one here and this one here. So that will be extra work. So we'll have our interval convergence, most of the time something like this. Sometimes it will be all real numbers also, and in special cases it will be only one value, but most of the time for us it will be an interval for real. So for all x's inside that interval, the series will be convergent. If we plug any x outside that interval, series will be divergent. Radius of convergence, that's something that we will be looking for also. So you see, as soon as I get this expression, x minus c, c is the center, r is the radius, so it's going to be quite easy to find. But in general, radius of convergence is half length of the interval of convergence. Just a note here, you see here interval of convergence is all real numbers, and we say radius of convergence is infinite. Okay, so this is a special case. Here, when the series is convergent only for one value, for the center, and nowhere else, then the radius of convergence is 0 because we only have a dot. So in general, we will have a real interval that is skewed, but those are like some extreme cases also. As I said, ratio test will give us interval of convergence immediately. Now the only part that we need to do an extra work is the end point, because maybe when we plug x equal to the left end point, maybe series is convergent, maybe not. We will see. And also if we plug x equal to the right end point, maybe series is convergence, maybe not. So what happens is we need to verify what's happening at the endpoints, each endpoint separately. So it could happen that at both of them the series is convergent, in both of them is divergent, or in one point series is convergent, in the other is divergent. We will see that only if we plug the value of each endpoint separately and we study the series. Now what we will observe also is those series at the endpoints, they are linked. One of them will have this general form and the other one will have alternating version of it. So this is just a common occurrence, so it's good to just realize when we plug one of these endpoints might get this series, and if we plug the other one, we will get alternating version. So that's what's going to happen most of the time. So let's see what's happening here. If I try to find the radius and the interval of convergence for this power series. So if I look what I have here, I have actually a geometric series. Ooh. So I don't even need to use the ratio test because this is a geometric series and I know already the rules for the geometric series. My first element is 1 and then the ratio is x minus 2. So for geometric series we know that series is convergent if and only if the absolute value of the ratio is smaller than 1 and it diverges otherwise. So we see that the center of the series is 2, radius of convergence is 1 immediately here. So I just rewrite this inequality here in terms of intervals. So essentially x minus 2 is smaller than 1 but bigger than negative 1, and then I add 2 on both sides and I get this interval. So that means that this geometric series here, which is also a power series, is convergent for all values of x between 1 and 3. So whatever value of x I plug here, I'll get the convergent series. So whatever value between 1 and 3 I plug, series will be convergent. And since this is a geometric series, I also know what's the sum of the series. It is the first element, 1, divided by 1 minus radius. So the radius is x minus 2. Right here, x minus 2. So 1 minus x minus 2. We rearrange and we get this. So what does it mean? Well, it means that this geometric series, which is a power series, is equal to this function here, which is a sum of the series, for all values of x between 1 and 3. So whichever value of x I plug between 1 and 3, this series is convergent, and we know the sum, we just plug the same value of x here between 1 and 3. So what happens in 1? So if I plug x equal 1, what do I get? I get 1 minus 2, which is negative 1. So I get negative 1 to power k. So negative 1 to power k, if I try to see what's happening with the partial sums, I will realize that that series is divergent because the general term obviously is not going to 0. I have negative 1 to power k. The general term doesn't go to 0, so that part will be divergent. So what happens at x equal 3? If I plug x equal 3 here, I get 3 minus 2, which is 1 to power k. 1 to power k is 1. So I have series of 1. So 1 plus 1 plus 1 plus 1 plus 1. So that's obviously divergent. General term is not going to 0. So the series is divergent. So we just realized quickly that at x equal 1, the series is divergent. At x equal 3, series is divergent. So the interval of convergence for real is 1 open, so 1 not included, up to 3 open, 3 not included. And again, what matters is that this equality here holds for all values of x between 1 and 3, excluding 1 and excluding 3. Note that when I plug x equal 1, this equality doesn't hold. Okay? When I plug x equal 3, this equality doesn't hold. This is true, this equality is true only for x's between 1 and 3. Very important to realize. So this is an example with exponential. Later on we will find this series. So let's say another example. I have a series here, which is a power series, and I would like to know what is the interval of convergence and what is the radius of convergence of this series. So what we see is a series a little bit complicated. Here x to power k, so that's how we know it's a power series. Immediately we know that the center is 0, right? It's written here. So how do we proceed to find the interval of convergence? We use the ratio test. So the general term here is this, and we use a k plus 1 divided by a k in absolute value, and we try to find the limit and see when this is smaller than 1. So we compute limit when k goes to infinity of ak plus 1 over ak in absolute value. So we just plug the things, they will simplify a little bit. Now what matters here is to realize that the limit is with respect to k. Okay, so x and 3, they don't depend on k, so they can be taken outside of the limit, so it's easier to see what's happening because limit is on k. So what matters is what's the behavior of the expression when k goes to infinity. Nobody cares as of now for x yet. So this limit here is 1. That's cute. So at the end, this limit is equal to absolute values of x over 3. Now we know by ratio test that our series will be absolutely convergent if this limit is, so the limit to be computed is smaller than 1. Good, which means that this series is convergence for all x's that are in absolute value smaller than 3, which means for x between negative 3 and 3. So immediately by application of ratio test, we know that this series is convergent for all x's between negative 3 and 3. Absolutely convergent, because ratio test gives us absolute convergence. Okay, so series is divergent outside that interval. Now, what ratio test cannot give us is what's happening at the endpoints, negative 3 and 3. So we need to study that a little bit. So for each of these endpoints, because these are endpoints of the interval, right? Interval is here. Interval converges negative 3, 3. So all x's between negative 3 and 3, if I plug them into my series here, series will be convergent. I might not know to what, but it's a convergent. Now I would like to know what's happening at the endpoints. Maybe series convergence in one of them, maybe divergence in both of them, maybe convergent in both. I don't know, I need to study one at a time. So here we can pick any one to start first, doesn't matter, we need to check both of them. So for x equal 3, so what do I do here? Instead of x, I plug 3 and I see what do I get as a series. So I get a series, so 3 to power k divided by 3 to power k plus 1. So k over 3 at the end, right? So I have a series that is 1 over 3 equal to summation of k. Well, k is 0, 1, 2, 3, 4, 5, 6. So if I keep adding that, obviously it's going to diverge. You can also say that the general term doesn't go to 0, so by divergence test, this series is divergent. Which means if I plug x equal 3 into the series, series will be divergent. Okay, so at this endpoint on the right side, series is divergent. What happens if I plug negative 3? So I take the series and I plug negative 3. Well, something similar happens. I will have this with negative 1 to power k. So essentially I'll have an alternating version of this, and general term again is not going to 0, therefore series is divergent. So in both of these endpoints, series is divergent. Okay, so to summarize everything, my power series is convergence for all x that is in interval between minus 3 and 3 open, because at minus 3 it is divergent, at 3 is divergent, so those two are not included into interval of convergence. Good, so we see immediately that the center of the series is 0, and now radius is 3, right? It's half length of this radius of convergence. Another example, again we want to find interval of convergence and radius of convergence of the series. What do? We use the ratio test. We compute the limit of the ratio ak plus 1 over ak in absolute value, and we know that this series will be convergent using the ratio test absolutely when this expression at the end is smaller than 1. So let's just replace things. It simplifies a little bit, and again recall you that limit is when k goes to infinity. So when we compute the limit, we need to have expression with k here, and everything with x can be taken outside of the limit in front, because limit is in terms of k. So here we simplify these two. So the limit here, what happens? Limit here is 0. Oh, so this is interesting. So I have 10 times x minus 1 in absolute value times 0, which is 0, right? Wow. So this means that whatever value of x I put, this expression here is equal to 0. Wow. So regardless of the value of x, this expression is 0. That means that by ratio test, the series is absolutely convergent for any value of x. X doesn't play a role at all. Wow. So the series will be convergent for all values of x. So what's the interval convergence? It's all real numbers. So interval is from minus infinity to infinity. And we said by convention, in that case, we will say the radius is infinite. So this is very interesting. Since the limit here is 0, I have 0 times this expression, which is 0, times 10, which is 0 again. So 0 is obviously smaller than 1. So by ratio test, this series is absolutely convergent for any value of x. Wow. So that was something. So let's see what's happening with another power series. Again, to find the interval of convergence and radius of convergence, first step is we apply the ratio test. Compute the limit when k goes to infinity. So this at this stage doesn't depend on x, it's just k. So here the limit is 1, so I have 1 times absolute values of x over 4. So absolute value of x over 4 needs to be smaller than 1. So when that happens, my series is absolutely convergent for those values of x. So I need to now rewrite this a little bit. That means that absolute value of x needs to be smaller than 4. So my series is absolutely convergent for all x's whose absolute value is smaller than 4 by ratio test. Very straightforward. Now the next step is to see what's happening when x is 4 or minus 4. So because here the interval is between negative 4 and 4, obviously. So endpoints are negative 4 and 4. So I need to test what's happening with the series when x is equal to 4, let's say, and then to minus 4 later on. So when x is equal to 4, I just plug 4 instead of x and see what's happening. So to simplify, I have a harmonic series, and I know that harmonic series is divergent. So my series, my power series at x equal 4 is divergent. So x equal 4 cannot be part of the interval of convergence. At x equal minus 4, I plug instead of x minus 4. So I have minus 1 to power k, 4 to power k, so 4 to power k and 4 to power k will simplify. And here I have minus 1 to power k over k. So we realize that this is alternating version of harmonic series. And we know by alternating series test that this series is convergent. So what do we learn now? We learned that at x equal 4, series was divergent, but at x equal minus 4, series was convergent. So finally, we regroup everything to get our final picture of the interval of convergence. So at minus 4, we are convergent, at 4 we are not. So all the values obviously of x in between, we are convergent. We know that by the ratio test. So minus 4 is included, so this is square bracket, is included in the interval of convergence, and 4 is not, that's why the bracket is open. Radius of convergence is still 4, radius doesn't change. The fact that one of the endpoints or both is included or not, the radius of convergence remains the same, it doesn't change anything. So our radius of convergence was 4, we found it here already, so the radius will not change. The only question is what's happening at the endpoints. So that's why we need to study situation at each endpoint separately. And what we just realized is, as we said before, one of the series has a general form like this and the other one is an alternating version. So that's what we had here. Harmonic series and alternating harmonic. That will be what's happening in general. This case is very special just to show you a little bit some of these, let's say, pathological cases. So if x is not equal to 5, then I can compute the ratio test properly, because obviously if I have x equal 5, I have division by 0, it's no good. So for x different from 5, I can perform my ratio test. So here I end up with something like this. So this limit, when k goes to infinity, when x is different from 5, this value here is different from 0, obviously. And then this part here is increasing forever. So the limit does not exist, right? Because the general term would be increasing. So that's what we have here. If x is different from 5, this value here is different from 0, and this part here is increasing without bound, so the limit does not exist. So we write it this way. So when x is different from 5, our series is divergent by ratio test because the limit is bigger than 1, obviously. In this case, doesn't exist even. Now, what happens when x is equal 5? Well, this thing here, when x equal 5, so we have 0 here. 0 to power k is 0, right? But we said in case of k equals 0, we have 0 to power 0, we will say it's 1. Right? No. Oh. So what happens here is we have a convergence only for one value of x. So that's why this example is interesting, because it's a little bit pathological. The series is convergent only at the center. And in this case, we said the radius of convergence is 0 by convention. So what happens is, since this series is convergent only at x equal 5, we could just plug x equal 5 to see what's happening. So we have this. So we said 0 factorial is 1, 0 to power 0, we said it's 1. And then after that, all the other terms will be 0. So that's why here by convention we have 0 factorial 1 and 0 to power 0, 1. So this will be 1 plus 0 is 1. So this series is convergent only for x equal 5. If I put any number different from 5, series is divergent automatically. So this is just a pathological case to show you a little bit. Here another version of it. Again, if x is different from 0, because we don't want to divide by 0, what happens here? If x is different from 0, again, limit when n goes to infinity, well, the limit does not exist, because this keeps increasing forever. So by ratio test, the series is divergent for all values of x different from 0, obviously. And now what happens when x is equal 0? Again, similar situation. We have this expression here. So again, 0 factorial is 1. 0 to power 0 is 1 by convention. So this series is convergent to 1 when x is equal to 0. And if x is different from 0, it is divergent. So these are just some pathological cases. So you can see different options for the interval of convergence. So just to summarize a little bit, we had this geometric series, which is also a power series, and we realized that the radius of convergence was 1 and interval was negative 1, 1. In this case, we realized that radius of convergence is 0 because series was convergent only for x equals 0. So interval is actually just one number, and the radius is 0 by convention. And then we had some proper case, let's say, and we realized that the radius was 1, and in one case the left end point was included in the interval and the right one was not. That happens after examination. Sometimes both of them will be, sometimes none of them, sometimes one of them. But we need to check what's happening at the endpoints. And then in this situation here, radius of convergence was infinite because the interval was all real numbers from minus infinity to infinity. So these are just cases that we can encounter. Open interval, just one point, all real numbers, and then this half open interval on one or the other side, or close on both sides depending on the situation. So this is just a little bit to have an overview of the possibilities. So again, another example, if we want to find the radius and interval convergence of this power series, again we use the ratio test, rewrite everything extensively. Again, the limit is when n goes to infinity, so don't forget the absolute values, and they go with x, absolute value x, super important. So now a limit here of this expression when n goes to infinity is obviously 0, so I have absolute values of x times 0 is 0, so this expression is 0 for all values of x. So by ratio test, this series here is convergent for all values of x. Wow. Which means that the radius of convergence is infinite and the interval of convergence is all real numbers between minus infinity and infinity, right? Now, an interesting case is the observation that these power series, which when they converge in their interval of convergence, they are actually functions of x. So that's why we write f of x. What happens is we can actually differentiate them and integrate them term by term. And the radius of convergence of the new series is the same as the radius of convergence of the original series. So that's funny because this looks like a polynomial, right? It's not a polynomial, but it looks like. So I can integrate this part by part, each piece with respect to x. It's not a problem. So I will get the integral of f equal to integral of this plus integral of this with respect to x, obviously, integral of this. So that will be quite straightforward. I could also differentiate my function, and I have the derivative is equal to the series of derivatives of each term. So essentially I have series of derivatives. So that's very particular for power series. So we can integrate them term by term with respect to x, and we can also differentiate them term by term with respect to x. And we still get a power series which has the same exact radius of convergence, not interval, a radius of convergence as the original series. Interval will be pretty much the same. It's the only question is what's happening at the endpoints. Sometimes endpoints we lose one or two of them, sometimes we gain depending on the situation. So interval remains pretty much the same except the endpoints eventually, and the radius remains the same if I integrate or differentiate the power series. So that's very particular. So derivative of my power series, I differentiate it term by term. So right, we have here pk, so that's a number, x minus c, c is a number, to power k. So if I differentiate this, k goes down, x minus c to power k minus 1, times derivative from inside, which is 1. So that's what we have here. So that it's straightforward, there's nothing special there. So essentially what we realize is that power series, I can differentiate them term by term, and I can actually just take the general term and differentiate it straightforward. There's nothing special there. And I get that this power series is equal to the derivative of the function that we had at the beginning. Fantastic. Similarly, we can integrate term by term. So the integral of my function is integral of the power series term by term. So essentially we integrate with respect to x. So integral here is k plus 1 divided by k plus 1, right? So nothing special, straightforward. Now the only interesting thing is we need to remember that when we integrate, we have a constant of integration and we will need to find its value. So don't forget to add k. My suggestion is to write k in front here, or whatever letter you pick for your constant. So k plus, and then you write the series. That would be maybe wiser, because that way you are sure that you don't forget the constant of integration. But with some practice it's going to be fine. So this is true for power series. We can integrate them term by term and differentiate them term by term and get a new power series with the same radius of convergence and pretty much the same interval of convergence. Maybe the difference will be at the endpoints. So that's phenomenal, and that's special to power series. Just to show you how special it is, so this example here is a series that is not a power series. And we will just show that in this case, even though the series is absolutely convergent, if I take the derivative of this series with respect to x, I'll get another series that is obviously not the power series, and it will not be even convergent. This is just to show you how special the result for the power series is. Because if I don't have a power series, I don't have this result automatically, right? So this is automatic for power series. I can integrate and differentiate it by term. It's fantastic. So example 8.5 is just there to show you that this series will be absolutely convergent, obviously, by direct comparison test with P series with P equal 2. So no issue at all for all values of x. So interval of convergence of this series is between minus infinity and plus infinity, so basically all real numbers. Now what happens if I differentiate the series, just to see, I get something like this, and this term does not go to 0, so therefore the series is divergent. So the series of derivatives is divergent. So you see, even though my original series, which was not in this case power series, just some regular series, it was absolutely convergent everywhere, but its series of its derivatives is not convergent at all. So this is just to show you that our big result for the power series is very special. So that's what it says here. In case of power series, you cannot have the derivative series is not convergent. It will be convergent in the same interval with the same radius. Again, interval will be depending only on the endpoints. Maybe sometimes endpoints are in or out, depending on the situation. So that's very interesting. Another interesting thing is that we could so now have our power series and then eventually differentiate it for fun. So here we will have our geometric series, and then we will manipulate it a little bit to get power series for these functions here. So this is very interesting and situation. So let's see how this works, just as curiosity. So I have my series here, which is alternating, but if I rewrite it this way, it is actually geometric series. So why is this useful? Well, for geometric series, I automatically know what is the interval of convergence, and also I know what's the sum. So that's the part that matters here for geometric series. I know the formula for the sum of the series. So obviously here radius is negative x, so I take absolute value. So for all values of x whose absolute value is smaller than 1, our geometric series is convergent. And we know immediately what is the sum. So r is negative x. So first term of the series is 1. So I'll have this expression here. So this is the sum of the series for x's between negative 1 and 1. So that's what it means. Our geometric series, or written as alternating series here, is convergent for all x's between negative 1 and 1. And we know the sum also is this expression here. Just to note that this series, when x is equal to 1, is obviously divergent, because then I have minus 1 to power k, so that's divergent. The general term doesn't go to 0. And if I have x equal minus 1, I'll have minus 1 to power k times minus 1 to power k. So I'll have series of 1, again, is divergent. So really our interval of convergence is open interval minus 1, 1. So for this geometric series or power series, and the sum is here. So this is the important part. we have the interval convergence of this geometric series, and we know the sum of the series. Again, the ratio was minus x. Now, why is this useful? Well, if I want to find the geometric series, or actually the power series for this expression here, I could use the expression that I have here for the geometric series and realize that I can differentiate term by term. I can differentiate this side and this side also with respect to x, and equality still holds. I could also integrate them and equality still holds because these are power series. So that's what is interesting about power series. Once you have one expression, you can integrate as many times as you want both sides, and you keep getting new power series and equality holds. And if I differentiate, I can keep differentiating forever, get different expressions on both sides. So I'll have different expressions here for function and different power series, and equality will be valid. So that's funny with the power series. So let's see how we can actually use this expression to get representation in power series for this function here. We remember if I differentiate the left side, I'll get something like this. So it's almost there. Obviously I differentiate both sides here with respect to x. So x to power k derivative is k goes down, x to power k minus 1, right? So that's what we have. It is important to keep writing the interval of convergence, because this equality here is valid for x's between -1 and 1. So when I differentiate, it's still valid only for values of x between -1 and 1. Okay, so I need to keep writing this just to remind myself of validity of this equality. When is this equal? It is equal for x's in interval of convergence. So now I have -1 here, so I multiply both sides by -1, and I get on left side what I need. If I multiply by -1, I'll have -1 to power k times -1, so -1 to power k plus 1. Not a big deal. So I have actually on the left side the function that they gave me, and on the right side I have a power series representation, and those two are equal for x's between -1 and 1. Wow. Similarly, I could try to find the power series representation for this expression here. So again, I start with my geometric series from our example. What do? Well, it's almost the same. It's just that here I have x squared. So if I replace x by x squared, I'm done. I'll get here x squared, and here I replace x by x squared. And here I replace x by x squared, obviously. I need to replace it everywhere. So I get on the left side my expression, I replace x by x squared, so not a big deal, so I have x 2k, and again x, I replace it by x squared, so this means x squared smaller than 1. Again, what are the values of x for which x squared is smaller than 1? X is between -1 and 1. So the interval remains the same. So this is very interesting. I have one series for which I know the sum because this is geometric series, and then I can integrate, differentiate. I can replace, instead of x, put another value. If I want x cube, it's not a problem. Instead of x, I put x cube here, and I'm good to go, and obviously x cube here. So you see, we can integrate, differentiate, replace x by an expression. Just from one series we can generate so many of these. So now obviously we recognize that this thing here is derivative of tan inverse. So that's why we say, okay, how could I get a representation series for tan inverse? Well, if you integrate this, you'll get it. So in previous example we found this equality here holds for x's between -1 and 1. And now if I integrate both sides, obviously integral of left side will be tan inverse. Oh, we need to remember that when we integrate, we have constant of integration, so plus c obviously. So integral on the right side. it's with integral with respect to x. So the sign doesn't depend, the summation doesn't depend on x, it's just x, the expression with x. So it's a series of integral of x to the power 2k with respect to x. So integrating this is not a big deal. So 2k plus 1 divided by 2k, right? So we have a series here that we got from the integration plus a constant, obviously. So tan inverse is equal to this power series for x's between -1 and 1. Wow. Now the last piece is maybe we'll need to find value for c. How do we find? Well, since this equality holds for any value of x between -1 and 1, so we can pick any number between -1 and 1. 0.7, 0.8, minus 0.2, but it is wiser to pick 0, right? Because it simplifies our expression. We want something simple. For any value of x between -1 and 1, this equality is true. So pick value of x that is simplifying your life. So it is wiser to pick 0. So tan inverse of 0 is 0, obviously. And here I plug 0, and I realize that all these terms are 0 plus 0 plus 0 plus 0. So essentially, right hand side is 0 plus c. And that means that c is equal to tan inverse of 0, which is 0. So c is 0. So finally, our expression for the tan inverse in terms of power series is this expression here. Because the constant is 0, so we don't add 0, you just keep it as is. And this is valid for all values of x between -1 and 1. So that's very interesting. Now, what happens is when we integrate, sometimes the endpoints will jump into our interval of convergence, because maybe sometimes when we integrate, series will be convergent at one of them, but we need to check. So what happens if I try to plug 1, I'll get an alternating series here. So x equal 1, this is 1. So I get an alternating series, and by alternating series test I can prove that this is convergent. If I plug -1, again I'll have at the end here -1 to power k plus 1, which is giving me again an alternating series. By alternating series test I can prove that that series also converges. So basically radius of convergence stays the same, but interval might change just a little bit. Maybe one or both of these endpoints might be included. In this case, series is convergent at both endpoints, so we could write that interval of convergence for this series is -1 included and 1 included also. Radius is 1, radius doesn't change. Interval, only the question is only the endpoints. So we have plenty of exercises that are solved on the slides. I will just illustrate a couple of them just to remind you of the procedure. So the question is always find the interval of convergence and find the radius of convergence of the power series. So what do? Well, we have a general expression. We use the ratio test, compute the limit when n goes to infinity of an plus 1 divided by an in absolute value. Absolute value is super important, don't forget it. So we rewrite the general term with n plus 1 and then divide by an, so you have double fraction, so I flipped it immediately. Here, reminder, limit is computed with respect to n when n goes to infinity. So x minus 3 doesn't affect this limit. So I will take absolute value and move it outside of the limit, in front, okay? Because that way I can see clearly what's happening. So I have x minus 3 that doesn't depend on n, so that's why I'm moving this absolute value outside. And then I have limit of this expression that contains only n. So limit here is 1, so I have absolute value times 1. And by ratio test, this is absolutely convergent if and only if this absolute value here of x minus 3 is smaller than 1. So now I need to rewrite this So that's x minus 3 smaller than 1 but bigger than -1. Then you add 3 on all sides, and then you get an interval here. By the way, we can immediately see that this series is centered at 3, radius is 1, right? So that's clear. Now interval of convergence is 2 to 4. So that's our initial thing, and that's what we got by the ratio test immediately. So we know by now the center is 3, radius of convergence is 1, and we found the interval of convergence, 2, 4 open. Now the next step is to see what's happening at the endpoint 2 and what's happening at the endpoint 4. Maybe at one of them, or both, or neither, this series is convergent. I don't know, I need to check. So for now, we know that the series is convergent for x's between 2 and 4, but let's see if we can have convergence at least one of the endpoints. Let's see what's happening. So if I plug x equal 2 in my expression here, x equal 2, I get 2 minus 3 is minus 1. So I have -1 to power n divided by n. I recognize this as alternating harmonic series, and I know this series is convergent by alternating series test. Oh, so x equal 2 is included now in our interval of convergence. That's cool. What's happening at x equal 4? If I plug x equal 4, 4 minus 3 is 1, so 1 to power n is 1. So I'll have harmonic series, and I know harmonic series is divergent. So in summary, what I have is that my power series is convergent in the interval 2, 4, but it is also convergent at x equal 2. So that's why I have here equal. So 2 smaller or equal x smaller than 4. So right, at 2 we are also convergent, but not at 4. So interval of convergence is actually semi-open interval, 2 included, closed, comma, 4 open. 4 is open because at 4 we are divergent. Radius of convergence remains the same. So the series is convergent for all values of x between 2 and 4, including the 2. If I pick any other value of x outside of this interval, so smaller than 2 or bigger or equal to 4, series will be divergent. This is straightforward application. So let's see, for this power series, we have x to power n, so this is a power series. Let's see interval and the radius of convergence. We can immediately see here that the center is 0, right? So by ratio test, we compute the limit when n goes to infinity of an plus 1 over an in absolute value. And again, x does not affect the limit. Limit is on n, so we can take the absolute value of x outside. So absolute value of minus 3 is obviously 3. So those will not affect the limit in n. So if I compute this limit, if I rewrite a little bit, I realize the limit is 1. So by the ratio test, I know that 3 times absolute value of x must be smaller than 1 in order for the series to be absolutely convergent. So I get immediately interval of convergence. Now, the last part of the work is to check if the series is maybe convergent at one of the endpoints. How do we do that? Well, we plug the endpoint into the expression and we see if the resulting series will be convergent or not. So for now, we know that the series is absolutely convergent for x's between -1/3 and +1/3. So let's see what's happening at the endpoints. So we plug one of the endpoints first and then the other. So at x equal -1/3, we plug, instead of x, we plug -1/3, right? Here instead of x, everything else remains the same. So I rewrite this and I get this series of 1 over the radical n. So if I remember this series 1 over radical n, if I rewrite it a little bit, oh, but this is a p series with p equal 1/2, which is smaller than 1. So this series is a p series with p equal 1/2, which is smaller than 1, which means this series is divergent by p-series test, right? So at the end point x equal negative 1/3, the series is divergent. Okay, so let's see what's happening at the point 1/3. So I plug 1/3 instead of x. So 3 to power n will simplify. I'll have minus 1 to power n. So now what I realize, I have an alternating series. Oh, alternating series. Maybe I could use alternating series test and check the two conditions. They are both satisfied. It's straightforward. We just need to write it out. So by alternating series test, this series is convergent. What does it mean? It means that my interval of convergence includes x equal 1/3, but it does not include negative 1/3, because we saw that for that value of x, series was divergent. So finally, my interval of convergence is open negative 1/3, because this part is not included in the interval of convergence, because we are not convergent at negative 1/3, comma 1/3 included. We just checked that we got an alternating convergent series at x equal 1/3. So interval convergence now includes the right endpoint. Again, radius of convergence remains the same regardless of if one or both of these endpoints are included or not. Radius of convergence remains the same. Radius here is obviously 1/3. So it's half length of the interval. And series is divergent obviously for all values of x outside of this interval. So anything bigger than 1/3 strictly bigger, and anything smaller or equal to negative 1/3, we would be divergent. Another one for fun. So this is, again, you see x plus 2 to power n. So this is a power series. We want to know what is the interval of convergence and the radius of convergence of this power series. Again, we use the ratio test. Limit is on n, so anything, all the constants go out, and all the expressions with x go out with the absolute value. Constant also, we apply absolute value always. So this way we have one part that does not depend on n with absolute values correctly written, and one part that depends on n, and we compute the limit for that. So here the limit is 1, it's straightforward. So by ratio test, we know that our power series here will be convergent if and only if the limit is smaller than 1. So we now rewrite this. So 3 goes to this side, so x plus 2 in absolute value needs to be smaller than 3. Now we rewrite the absolute value, the inequality with absolute value. So x plus 2 will be smaller than 3 but bigger than negative 3. Then we subtract 2 on each piece and we get this interval here. By the way, we see that the center of the series will be negative 2. X minus minus 2. So center of the series will be negative 2. Radius will be 3. Because x plus 2 in absolute value is smaller than 3, right? The radius will be 3. So our interval of convergence is here. We get it from the ratio test, straightforward. Now the last piece of work is to check if what's happening at the endpoint, if any of those endpoints is producing a convergent series. So we need to test both of them anyways. So let's start, let's say, with the left one, x equal negative 5. So here instead of x I plug negative 5. So I have negative 5 plus 2, which is negative 3, right? So here I rewrite it a little bit. So I have negative 1 to power n and 3 to power n. It will simplify a little bit. So I get a series like this. So I have negative 1 to power n times n. The general term here, if I check, n is increasing, right? So the general term here, the limit is never going to be 0. Limit doesn't exist because this thing is sometimes big positive, sometimes big negative. So basically by divergence test, I can conclude that this series is divergent because the general term is not going to 0. Okay, so minus 5 is not part of our interval of convergence. What happens if I plug x equal 1, so the right end point? So 1 plus 2 is 3, so I have 3 to power n. So I again simplify, I get this. So obviously this expression, I add 1 plus 2 plus 3 plus 4 plus 5, obviously this is divergent. Also you can say by divergence test, the general term doesn't go to 0, so by divergence test, this is a divergent series. Therefore, finally we have that our series is convergent for all x's between -5 and 1 open, right? Because none of those is included. Again, the radius remains always the same here, regardless of if endpoints are included or not, radius remains the same. So our series is convergent for x's between -1 and 5, -5 and 1, but it's divergent for all other values of x. You have plenty of other solved examples. You can go through them. It's always the same procedure. We write the general term, we fix it, and then we apply the ratio test with absolute value, don't forget. Compute the limit. Limit is on n, when n goes to infinity. And then we'll get our initial guess for the interval of convergence. And then we test each of the endpoints separately to see if series is converging in any of those endpoints. So it's pretty straightforward, not too complicated. It's just an application of ratio test. Again, these power series, we know that we can integrate them and differentiate them on their interval of convergence, and we will get another power series. Very beautiful. We will see application of that later on. So please go check. We have plenty of other solved examples on the slides. Just go through them and see a little bit, try to solve some of them. Solutions are there.